All right, good evening, everybody. Welcome to another edition of vBrownBag. We are continuing our VCAP6 design series tonight, and we're going to be diving into virtual machine configurations, talking more on the physical design. So this evening we have the lovely Mike Burkhart, who you can find on Twitter at vMikeB, and then myself, Rebecca, and I'm here simply to press record and to make fun of Mike when appropriate. So, feel free
So
to
always.
always. Um, every slide, I'm going to be heckling. And so, feel free to please join in on the conversation. You can ask questions via GoToWebinar, and I will relay those to Mike. Or, of course, join in on Twitter using the hashtag vBrownBag. Don't forget, we also have other recordings besides this lovely EMEA channel that we are hijacked for the VCAP series. Tomorrow night we'll continue on with the US, and then Thursdays we have the Latin American series. So to begin my heckling, I want to be judged on whether Mike and I did it better or whether the original Jack and Rose did it better.
Look at that. That's beautiful.
I
That
know.
is majestic right there.
Personally, I think Mike and I did it better, but I will leave that up to the general population to decide. So without further ado, I'm going to turn it over to Mike. So I'm going to stop sharing my screen and change presenter.
All right.
Magic. Magic Mike.
Magic. All right. Let's see if I can do from beginning. You see my screen? Get the.
I can see it.
All right. Good deal. So thanks everybody for joining. VCAP6-DCV design. Section we're working on right now is 3.5 VM config for the physical design.
Do you wanna
As
do you wanna press the
oh,
play?
you're not seeing.
I'm
Are
seeing
you not seeing the
no, I'm
That's
seeing
two
the
screens.
slideshow. I'm seeing more of the presenter side.
Yeah, hang on one second.
This
Let
whole
me
dual screen thing.
yeah. Nope, that doesn't come up either. Let's see if I can swap screens real quick. Okay. Let's try one more time.
There we go. Now I still see the presenter view.
Let's swap those displays and get this going. There we go.
Magic. Now it's working.
Fantastic. All right, now we're rolling. So thank you, Rebecca. And thank you guys for joining. So I'm Mike Burkhart. I'm a senior solutions architect with the head Chicago VMUG leader. You can find me on Twitter at vMikeB or vmikeb.com for my blog. I am an endeared member of the VCDX Wolf Pack, of which Rebecca is a member, and other VCDX, newly minted VCDXs, soon to be myself, hopefully. Learner, teacher, burner, reacher, and also alligator handler. So you may recognize that shirt. This is from the same trip that we took, and I got to hold an alligator. So excellent. So going on, what are we going to do here? Skills and abilities for the DCV deploy here. Using RDMs and virtual disks, VM memory, basically everything that comes along with a virtual machine. So your 4 food groups: CPU, RAM, disk, network. We've got latency sensitivity. We've got clustering, even going down to the level of, what can we do to support a virtual machine in either larger capacity or performance. Even how do we get it from one data center to another? You're using ISOs and templates in a content library. So we got an exhaustive amount of material here. I won't belabor the point. We'll just go on right ahead. Starting out with this, you may have seen this slide before. Our design process for the DCD or for design, we begin with assessing our current technical and business requirements. Requirements gathering is number 1. All of those inputs are taken into consideration. They're moved into a design, so to speak, a high-level logical container, which validates and fits all of those needs and constraints and risks and assumptions as well. Then we move on to a deploy phase, ensuring that from the logical design, we move on to a physical design and committing those into an actual state where we can configure and touch, etc. And then validation is also a key factor in day 1, day 2 operations, ensuring that we met the requirements of the design and that we're successful. Here, design methodology, like we just said, risk constraints, assumptions, and requirements. We start out with those, move to conceptual. Logical is reliant upon that. So those arrows pointing to conceptual, everything is reliant upon this, this gathering of business objectives, requirements, etc. We are on the right-hand side of the physical layer, so we are actually making design decisions and implementation. So,
man, that's a beautiful slide. It's like it was artisanally handcrafted by me.
I think it was actually a free-range organic or handcrafted. It's definitely a Rebecca Fitzhugh slide.
It's beautiful, Mike. You do it better.
That's true. I did change colors. Moving on. So, jumping into more things that Rebecca did. Analyze the use of an RDM or virtual disk. So, first we'll start out with a virtual disk. That's VMware's bread and butter is a VMDK. Comes in 3 different flavors. Thin provisioned, you've got only the space that is written to is allocated, plus a little bit of buffer. Upon writing, that virtual machine will request disk writes, and in turn, the ESXi kernel is going to allocate more storage on the fly. When it does that, there's actually a bit of a performance hit. It's negotiable. It's not necessarily this huge, OS shattering sort of moment, but for latency sensitive VMs, you want to make sure that thin provisioning may not be your first choice. But it does allow you to have only the space needed, right time, right place, right? So just in time, most people have heard this term. This is just in time storage. So you can oversubscribe your data stores if you thin provision every VM. So be careful with that. Monitoring is a must. Thick lazy zero, I provision all my storage. So I allocate all storage out, but I do not zero all the storage. Reason being, I want to create this disk, want to get it out the door. I also want to protect its capacity, but I don't want to go through the process of waiting for it to be zeroed out before I can start using it. So it's kind of a middle ground between thin and thick eager zero, which we'll get to. The protecting of capacity is not necessarily too, it's not too crazy of a thing. It literally just creates disk boundary, and when you allocate that disk, it just partitions out the space on the VMFS data store. So thick eager zero, same thing as thick lazy zero, only when I create that disk, it's going to create those disk boundaries, and it's going to zero out the VMDK before it's used by the virtual machine. This is the most performant of the disk types because there is no waiting on disk zeroing or disk allocation from a capacity standpoint. But on the front end, you take the longest to deploy it. So to keep that in mind. So, when I'm deploying, if I want to deploy fast, thin provision would be the quickest. But if I'm deploying for performance, thick eager zero may be, my go-to. And, thick lazy zero may be an in-between good middle ground. So we have independent and dependent disks. So independent, what this means is that it's independent from the snapshot chain. So snapshotting is basically taking a point in time from a virtual machine disk and making that disk read-only, creating a Delta file. And that Delta file is now the write file, so to speak, the write VMDK. Any reads pass through both the Delta file and the original snapshotted volume. So if it's independent, a disk is independent of that snapshot chain, and it will not partake in that process of snapshotting. So it won't be bothered by that. The great thing about this is now we have a disk that is never going to be read-only or paused or anything of the sort, aside from one of these options here. Persistent is a no Delta file. We commit everything to disk, so we never take snapshots. We commit everything straight off. There's no possibility of really messing with that disk. It's just power on, read data, write data, power off. Non-persistent is actually a very interesting option where I write to a Delta file, but the initial disk is all read-only. When I reboot, that disk is wiped and reset. So keeps the disk pristine. So if I ever have any sort of data that I want to keep in its initial state, non-persistence perfect to that. Dependent disk is dependent on the snapshot chain. The reason that these are important here is that snapshotting is important for backups. So vSphere API for data protection. Normally, you're going to see backup proxies and backup appliances leverage snapshotting. That's the go-to mechanism for creating a backup. It's one part in the process. It's not the only mechanism, but just so you're aware. VMDK versus raw device mapping. So we heard what VMDK is. Basically files existing on a VMFS data store. Raw device mapping, or RDM, you have semi-direct or direct access to the LUN from a SCSI command perspective. So if I have a virtual mode RDM, then everything that I say goes through the VMWARE kernel. So ESXi has visibility into everything that I send, except for reads and writes, which we want to be quick, so they're sent directly to the array. But anything like SCSI2 reservations or all LUNs or any sort of command, that's all go through the ESXi kernel. This helps us in many different ways because we can go through the vStorage API or the VADP API and directly link into that RDM. So that raw device mapping in virtual mode, we have some control over from a vSphere perspective. Physical mode, we have almost no control because that is directly linked through, essentially around the ESXi kernel, and it goes straight to the virtual machine. There is a mapping file for both of these types of virtual machines. What's different is the mapping file for physical mode is really only going to be a type of header and kind of sectors, tracks, disks, etc. Geometry for that LUN, whereas virtual mode will have a lot more of the vSphere credentials and metadata that you would expect out of a VMDK. So that's kind of like a VMDK there. But physical mode, if I have any sort of in-band management for storage, or if I have any need to directly connect to a LUN, if I'm physical to virtual clustering, that is one of the only ways to accomplish that today. So we may have already went through this, but just to kind of reiterate, VMDKs usually general use case. VMDKs are the most flexible. You can storage vMotion them around, you can back them up, you can cold copy, a lot of different flexibility with VMDKs. 62 terabytes or less is a maximum. And then we don't really have any special characteristics that we need from VMDKs. So there are some caveats, and those are a little out of scope for what we're talking about here. But for the most part, VMDKs are great for a large swath of your use cases. Virtual mode RDMs, if I want to do cluster in a box or across boxes, so that's Windows failover clustering services, or virtual machines that I have to use snapshots for as well. If I have to have some type of, if I have a vSphere backup mechanism, say rubric, etc.
Represent.
There's going to be, hello. So that leverages the VADP API going straight through the vSphere APIs, and that's going to be required for backing up a virtual mode RDM. Physical mode RDM, you can't have that. Caveat here, so I wrote larger than 62 terabytes, but really the larger is quote unquote large-ish. You get 64 terabytes out of a physical mode RDM, so that's 2 terabytes extra, but if you need it. In-band storage management, physical to virtual clustering, a lot of use cases here that we can really leverage. You cannot use NFS for RDMs. So I wanted to make sure we emphasize block-based storage. You can use RDM because it is directly contacting a LUN. So I'm claiming a LUN to the virtual machine. I cannot do that with NFS because it is a file-based storage protocol. So that does not work.
That's an excellent point. Another point that I'd make here is notice the specific use cases that Mike gave, none of which were better performance. I think that's like a big myth that we hear a lot in the field is people will tell me, well, I chose an RDM because I get better performance, and that's unequivocally false. Uh, at best, you'll get equal performance to a VMDK. In most cases, you won't even get that. So if you're looking for performance, it's going to be VMDK all day.
Absolutely. And it's a great point. The best use cases I really see for RDMs are more old school clustering. There are healthcare application suites that leverage RDMs as, they snapshot LUNs as a backup process. That's the only way that they have a backup approved methodology. So performance is a non-issue. If you need 64 terabyte capacity, that's when I'd go physical mode. And then, like I said, virtual mode is great for inter-VM, intra-VM clustering. So yeah, great point. So going on to virtual machine memory management techniques. So this is one of my more favorite topics. We do some really cool stuff with memory in vSphere. So TPS, transparent page sharing. Rebecca once told me that it's not transparent page file sharing.
You kept saying that.
I did, it's true, and I learned it that way, but that was in like the 2.0 days. So I'm still looking for the one document that ever said that. So anyway,
you're wrong today.
Oh no, I'm right today. I'm so right. Look at this. Look
you
at
did say it correctly today. I'm very proud of you.
I know. I'm proud of me too. Thanks. So TPS enabled by default in all memory states. So low, high, demands, soft, hard, and clear. Memory states we're not going to get into. You guys can look them up online if you'd like. But TPS allows the ESXi kernel to reclaim duplicate memory pages. How does it do that? What is the mechanism? There is an algorithm that the ESXi kernel runs every 60 seconds, and it scans physical memory pages. And if those physical memory pages are identical, and it uses a hashing, it uses a hash, basically, a hash comparison to ensure those memory pages are exactly identical. If they are, I remove the secondary, tertiary, etc. copies, and I create a 512 byte pointer straight back to the original copy. That only happens when I'm not using large pages, which is common with most operating systems currently. Large pages are a great way to have a large amount of RAM, and they're smaller translation lookup buffers for large pages. So it's a great way just to increase, we had a 2 gigabyte minimum back in the 32-bit days. I can't remember if that's Windows 2003 or 2000 something. Anyway, doesn't matter. So anywho, large pages were a response to that. They're way more efficient, but we cannot dedupe large pages. So anywho, even if there's no contention, we use this as a memory reclamation technique. Right now, as of 5.5 update 3 and 6.0 update 2, salting was introduced. Salting is basically making the UUID value of a virtual machine its default identification when TPS is enacted. So TPS is going to look at that salt ID and say, okay, who else has the salt ID? I can deduplicate your memory pages. So right now, by default and on any default install, you're only going to deduplicate inside that same virtual machine. So there are still some memory benefits, but again, you'd have to modify the salt parameters and say I have a entire cluster of Windows 2012, all the same image. I know for a fact part of their working set is going to be exactly the same. Great, I can dedupe the heck out of those things. But I need to change the salt ID, and I need to ensure that I'm not using large pages if I want to use this mechanism. Moving on to ballooning. So, well, actually, I heard you Inhale on that one. We're gonna use TPS later on too. I got you.
I was just gonna say that you have a great point when it comes to not sharing large pages. But of note, for those who are interested in learning more about transparent page sharing, during one of the states of contention, which I believe, I could be wrong here, but I believe it's low by default. It will actually break up large pages of memory into small pages of memory in order to try and share it as one of the mechanisms for reclaiming.
Come on, homie. I was going there.
Dang! Stole your thunder, fool.
Savage. Ah, well, that's what it is. And this is ballooning actually enters into the low state. So hit the nail on the head, segued right into there.
Word.
High five.
Yeah.
So what we do, we're getting contention on the physical RAM. It's a certain amount. This is a percentage, and there's a calculation. You could actually look it up if you want. There's a clear is a memory state where 28 gigs of RAM plus 1% of the overage that's a clear memory space. If you move down less than that 28 gigs plus 1%, then you're going to enter into a soft memory contention state, and that's when ballooning starts to happen. So we start breaking large pages like gangbusters because we need more capacity. Large pages are very highly performing, but we're going to start breaking those apart and deduplicating them through TPS because we're really looking for the space savings at that point. VMEM's control, that you're going to see vmemctl.exe is not a virus. It's not anything weird. It is the process that helps ballooning happen. Don't kill it. It starts pinning memory pages, and basically those memory pages stay within that vmemctl memory space. They don't get paged out. So the guest OS then is allowed to decide anything that's not pinned, I can swap that out to my own page file, swap file, etc., dependent on OS. Then your physical RAM, all of a sudden you're starting to get these free memory spaces because as you see on the right, stage 1, no contention. Stage 2, I'm ballooning my memory and spitting out the rest of it to some OS swap space. So now I've got the OS writing to some swap, so some of its memory is actually freed out the back door through VMware Tools. VMware Tools is a requirement for this. If you don't have VMware Tools installed, ballooning will not happen. So best practice, install VMware Tools. Next, what happens when I have ballooned most of my space up and I enter into a hard contention state, I'm still under contention and there's not much more I can do about it. I'm going to start compressing and zipping memory spaces. So if I can find a memory page that can be compressed to 2 kilobytes or less, I'm going to compress it. I'm going to throw it into the compression cache for that virtual machine. And that way I know I've still got the memory sticking around. I'm still in an up state. I'm not blue screening. I'm not denying memory. But also I'm freeing up 2K portions or less here and there. So this is a very granular sort of state. You can see where there's a bit of urgency right now. Before we're just kind of, stealing from Peter to pay Paul with memory with ballooning. Now we're really starting to squish things down and shove them into a tiny box. So mentioned here, compression cache is 10% of the virtual machine's allocated RAM. That's a modifiable advanced parameter. I don't recommend it unless you know what you're doing there. One of the last mechanisms here is swap. So you may have seen the vSwap file on vSphere data stores. The physical memory pages are now sent out to the vSwap file on the data store. We're going to see later that there are ways that we can help kind of soften the blow from that performance hit. But again, this is just another mechanism to ensure that keep the virtual machines alive and keeping the ESXi host afloat. In the worst case scenarios, the kernel itself, the hypervisor, will start paging out and swapping its own RAM. That's because it's trying to prevent a purple screen of death. If a PSOD happens, all bets are off, right? That ship has sunk, all the VMs are dead, I've got an HA event happening. So Mentioned down here host local swap cache versus a shared data store. We'll get into that a little bit later, but we have some mechanisms to kind of, if we know we're going to be over provisioning, we can kind of direct our swap cache to benefit us a little bit better. So when do we use these? What's the use case for it? TPS is always, and it's inter-VM, so it stays within your virtual machine because of that salted UUID. If I'm overcommitting RAM on purpose, which again, benefit of virtualization, I can really ramp things up, I can really overcommit, and I can run hot and heavy. I'm going to break large pages and change the VM images to the same salt ID, which are advanced parameters. If you do it at a large swath, you can just use power CLI and change all the salt IDs. Why would I do this? VDI is a perfect use case for this. I've got Windows 7, Windows 10 images galore. Now all of a sudden, I know those images are exactly the same. I dedupe all of the memory pages, and I can fit tons of desktops on a single host. So single OS or image clusters as well. So example I gave earlier of Windows 2012, if I have a cluster of 16 hosts and they're all Windows 2012 and I want to overcommit RAM a little bit, I can use TPS to my advantage, or dev test clusters as well, right? Don't want to spend a ton of money on dev test or maybe lab. Perfect use case there. Ballooning is natural. Talk to your parents. It's not a problem. The issue with ballooning is that if it's constant and severe, it can be indicative of a larger issue unless you designed on purpose to start ballooning at a certain point. So as soon as we reach between ballooning and compression, that's where we start winding up in large performance hit area and definitely in swapping. But that said, use cases abound for VDI, non-prod, dev test lab, remote sites, etc. So once I start into compression, I'm really going to start seeing, memory is going to be at a premium, and I'm going to notice the difference. Once I pass that, I'm writing RAM pages to disk, and that's going to be one of the final steps, right? I mentioned down here, if blocking, we could see a kernel panic in the guest OS. So if a guest operating system has already paged out to disk, it's already been balloon swapped and compressed, and it's asking for more RAM, it can experience a denial of service on RAM and blue screen. So that is possible. If that happens to the host, like I said before, purple screen of death. So good times, good times. Determining the significance of VM swap location. So 3 different places. We can keep the swap files with the VM files. Default selection, it's easy to manage. Just click next, next, next. I've got my disk. That may not be desired depending on if I'm replicating disks on a LUN. So in a DR scenario, I may not want to replicate my swap files, right? So in which case I can keep on a separate shared data store. So, if I want to vMotion, storage vMotion virtual machines around, separate shared data store is going to give me a little bit more leeway there. And then also I keep my virtual machine files on a regular replicated LUN. When you're designing for memory overcommit, this is where I was talking about before. We could have a different tier of storage where we could say, well, we know we're going to be swapping eventually, so let's put it on SSD. Or there's a host local swap cache we'll get into later. Well, right at the bottom. Those are going to be host local SSDs contained within the same server. So your swap's going to be lightning fast versus a shared SAN and NAS. You're talking about microseconds of latency versus milliseconds. So we don't have to reach very far to get those data blocks if we're swapping. The issue here is that I'm increasing vMotion lead time because those are non-shared data stores. So vMotion literally has to perform a stores vMotion operation and move all those blocks from one host swap cache to another before I can actually move that VM. So it'll impact vMotion a little bit. Latency sensitivity. I've already brought up a couple things about latency sensitive workloads. Let's dive into them. So determining latency sensitivity requirements. Yeah, we may or may not run into these a lot depending on what you work in. If you work in financials and high frequency trading, you may see this every day. If you have VoIP or e-learning initiatives that have to be no jitter, no lag, you may work with this on the regular. Some engineers may never experience working with latency sensitive workloads. The important point here I want to make is that you have to identify which resource or resources are sensitive to latency. Because I can't just say, oh, this VM's latent sensitive. Let's click the checkbox on this is a latency sensitive VM. That's what that's for, right? No, that is not. It's only for CPU when we identify it in the appropriate area, and there are other mechanisms we can use. So CPU, RAM, network, disk. How do we identify it? Are we trying to hit a certain mark of response time or round trip time? And then also, what's my average and what's my peak? What am I shooting for? So how do I hit that requirement? SMART method is perfect. Specific, measurable, attainable, relevant, and time bound. So here I made the example of, well, okay, I'm network sensitive. I got a VoIP server it's got to pass on all the bits and bytes over the network. I need less than a millisecond round trip between VMs. DRS rules can wrap around those VMs and keep them on the same host, so I don't have to actually hit the network. I can use the actual bus on the server itself, and the virtual machine processes talk directly to each other, so minimal latency there. And then the hours are bound between 8 and 5 business time. So I know when I have to hit those targets. I know how I can, what I'm going to need to do it. And then lastly, day 2 operations. What am I monitoring with? So how can I ensure that those are enforced and met? So the sensitivity requirements, I expanded a lot on these. I'm not going to go through all of them. But again, how we can kind of meet these different areas for the 4 different food groups. Server power is big. So on the bare metal server, I need to ensure that its power state is maximum or always on or whatever feature that says it's all voltage all the time. Disable my C states, that's sleep states, S3, etc. Disable all of the stuff that would ever impact that physical server from either going down or going into a low power state. From a virtual machine side, we need to know our NUMA nodes. So how many sockets, how many cores, how much RAM is dedicated to how many cores, etc. Understanding that, knowing that I'm not going to cross NUMA node boundaries, and good to know there. Reservations as well, making sure that all my megahertz are cordoned off. So, and then there's that latency sensitive advanced parameter. RAM, NUMA nodes, reservations, ensuring the physical design is met there as well. And then network's a little more specific. These are all, I recommend you look those up if you ever have to use them. Direct path IO is grabbing physical hardware, attaching it to the virtual machine directly off the PCI bus. Large receive offload and TCP segmentation offload also takes workload off of the virtual machine, allows the physical hardware to do it. So better utilization of resources there. And then moving on down to storage, para-virtualized SCSI drivers. So drivers are also huge in this space. Para-virtualized SCSI drivers can hand off read-write requests to the hypervisor and ensure a more efficient storage flow. So highly recommended on any sort of latency-sensitive workload. And then storage I/O control, and you saw network I/O control above. And then last but not least, I think it's important to note that hyperconverged infrastructure can potentially help with latency-sensitive workloads. Reason being that's compute node local storage. So I'm a big fan of hyperconvergence. HCI is kind of one of my wheelhouses. Everybody that knows me is, pretty certain about that. So it is one of those architectures that provides, the right time, right place, right storage etc. So I'm a big fan of using this for workloads that have any sort of sensitivity storage. So moving on, virtual machine features based on logical, functional, and application requirements. What the heck do we even mean? What does that mean? So logical requirements, you may have seen in some of the previous vBrownBag discussions on design. What does a VM do? It's either functional or non-functional requirement. So a functional requirement is, how am I going to do a something? I must provide adequate resources for the virtual machine to run. That's kind of a no-brainer. I must be able to back up a virtual machine through X mechanism, right? Avoiding downtime, removing all non-essential virtual machine hardware. It doesn't tell me what I must do, or it tells me what I must do. It doesn't tell me how I must do it, but it tells me, here are the things that I'm looking to accomplish. And then non-functional is, you must do it this way. So my operating system must be AD authenticated. VM must have X amount of RAM, Y amount of CPU, must use fault tolerance. These are all things that are constraining my requirements. So my design in non-functional requirement terms is actually a constraint. So those are basically the logical requirements high level, or how to suss those out rather. Application requirements are a different story. So from that same standpoint, it's, what does the app need? So I know what the business needs. What does the app need? Well, maybe I need a certain amount of storage, and it needs to be, certain amount of I/O from a performance standpoint. Maybe I'm required to partition disks to a certain layout so that a database storage is met by vendor specifications. Not uncommon, right? Maybe I need a multi-home NICs. I have to have 2 or more network cards on this virtual machine, multiple networks, et cetera, et cetera. So those are all our app requirements. We need to understand those as well, because those come into the virtual machine requirements. So that was pretty high level, but again, there are many different ways to ask those questions. Moving on to virtual machine best practices and sizing. First, we want to start out with easiest best use case. If it exists today, capacity planner. VMware Capacity Planner is normally a partner tool. So if you have a VMware partner, or if you want to contact VMware directly, Capacity Planner will basically take the virtual machine profile, or many virtual machines, examine them for performance, capacity, overtime, get all of those metrics, and tell you exactly what size that workload needs to be. It'll even tell you if you have more demand than that. You can also see these things in vRealize operations as well. So VROps is another great tool that if you already have that in-house, it will analyze the sizing and demand capacity for you. If we don't know what that workload looks like today, then first we can start off with manufacturer's requirements. Not a huge fan of doing this, but you can. Allocating adequate resources and understanding that, if I put this into my lab and they're telling me it needs 4 vCPUs and 16 gigs of RAM, okay, fine. I'll deploy it as such, but I'm going to monitor and I'm going to right size. I always have the ability to take away resources. It's not very easy, but it is possible. Does require downtime in some cases. But again, right sizing virtual machines starts out with knowing the workload, understanding how that fits, understanding if it's performance versus capacity trade-off, and really starting to shape up that box. So how many cores do I need? What are my gigahertz requirements, right? So do I need a peak workload? Do I need to size for average? Do I size for a certain percentile of the peak? With RAM, is there a certain CAS latency I need on chip? Do I need to protect that RAM? Is it adequately sized for what workload? So from disk, you got IOPS, latency, and capacity. So what's my IO profile? How many read versus write? How large of a disk do I need? And, or disks, plural. And then how responsive are they? And then network bandwidth, round trip latency, number of NICs, multi-homing, network design, that type of thing. So moving on, we're chugging right through here to reservations, shares, and limits. Just as a refresher, reservations are a guarantee. So just hopefully you have made dinner reservations before, and hopefully you have been guaranteed that table. If you haven't, I apologize. I hopefully did not take that table from you. But that's a guarantee of resource from a vSphere perspective. The way that we work around not reserving everything is that we have shares. So if I don't want to reserve everything everywhere, and I don't want to make it like it's a ton of physical virtual machines, so to speak, I can use shares. When under contention, virtual machines can say, hey, I get this many. So one virtual machine has 1,000 shares, another has 2,000 shares. Well, out of 3,000 shares, the second virtual machine gets 2/3 of whatever resources in contention. First one gets 1/3. So that's how that's compared. But only under contention. And then limits are a maximum upper boundary. So let's say I have an older operating system and I've got brand new smoking CPUs in my data center. And I know for a fact that this VM does not need anywhere near 3 gigahertz, 3.4, 3.7 gigahertz of CPU. I can put a limit on it and say, nope, you get 2, you get 1.5, you get 1. That way I know I'm right sizing. I'm still providing it with adequate resources, but I'm also not denying other virtual machines space. So if you want to mess with developers in your development cluster, you can allocate all their VMs with limits of 1 gigabyte of RAM or less, and everything writes directly to swap. Because that, you told it to. You said, well, you can have X amount of physical RAM, but above that, you don't get it. So it'll write it directly out to disk. Can use that for oversubscription, but I like to do it for messing with people. So how do I figure out how to use these? Is it necessary to have a bare minimum of X resource? Do I need to have some sort of mechanism to cordon off and prevent overuse of a resource? Is there a need for, do I expect contention? And or if I don't expect contention, how do I know in the event of a host failure, multiple host failure, problems in a cluster, etc., that I can guarantee at least fairness amongst resources? So that's your reservations, shares, and limits in a nutshell. I put down here that CPU is measured in megahertz, RAM is in megabytes, disk is in IOPS for storage IO control, and network is in megabytes or megabits per second, my apologies. And that's network IO control. So based on an existing logical design, so here again, we're in the physical realm, we're configuring, we need to know, how do we determine what that physical layout is going to look like for virtual machine hardware based on the logical design? Well, first off, what is the virtual machine hardware? So those of you that have taken an ICM course, those of you that have seen different blog posts on virtual machine hardware configuration, this is boilerplate for, this is what virtual machine hardware looks like. I'm not going to read all these off to you. Needless to say, we have a plethora of options. So El Guapo would agree. Also, El Guapo would know that this is probably way too many to use all at once unless we really needed it. So how do we take all of these options, boil them down into what a logical design really needs from them? First off, I'm going to start out by saying, use the least amount of hardware. You're going to meet your requirements. You're still going to use whatever mechanisms, whatever virtual machine hardware you need. That said, there are lookup tables, there are translation buffers, there are all sorts of things from the kernel perspective that look at the virtual machine and say, well, you've got all of this hardware. I've got to pay attention to it because it may execute some sort of I/O. It may have some sort of need. So the way that you reduce that the ESXi kernel being ADD, I suppose, would be to reduce the amount of virtual machine hardware. So just as kind of a taste tester, think about removing floppy disk controllers. Most people don't even use them. IDE controllers if you don't need them, right? Making sure you're using the right amount of RAM, vCPU, vNICs. Make sure you're not over provisioning on disk or provisioning too many SCSI controllers, etc. So just like Kunu says, do less. So good example of logical design. So I need to connect to a management and production VLAN. I don't care how I do it, but I need to make sure that network is available to this virtual machine. So a way to accomplish that would be 2 vNICs, one to management, one to production VLAN. Job done. I can go home now. I could also have 1 vNIC, and then I have the management and production VLAN routed upstream on some sort of physical, layer 3 device, etc. That's great for me, but that may pose a potential security risk for the business. So, attacking these problems in different ways proposes different design choices and different trade-offs. High gigahertz use application. How many threads and cores? I can assign, 12 cores. Great, but 12 cores at 3 gigahertz apiece ends up to being a lot of horsepower. What if it only needs 12 gigahertz? Well, I really only need 4 cores at that point. But that question of threads comes up. How many threads can I use at the same time? So how many CPU threads am I going to try to execute? So we need to pay attention to this application workload need and balance that out of performance versus allocation. Snapshot-based backups. Independent disks are out. Physical mode RDMs are out. We already discussed how those work earlier, and immediately eliminates those disk choices. So, and then I added in USB security dongle, and then application requires a partition layout. So USB security dongle can be considered a constraint. That's going to tie a VM down to a specific configuration. And then application requires partition layout, also a constraint. Other considerations in this realm of building out virtual machines. So CPU affinity, do I have any sort of CPU licensing? Do I have any need for CPU masking? So do I not want to use all of my processor's execution for any given reason, right? Maybe the operating system doesn't understand it within the VM. I've noted that EVC mode. EVC mode on the cluster is actually going to be the way to blanket all of this off for all the virtual machines. So CPU masking is on a per VM basis, so trade-offs there. Hot adding and RAM. If I need to add RAM on the fly, I've got an option there, but do I need to? Network, I've got options, lots of network cards I can use through, even single root IO virtualization. So I can take a physical network card and split it into many on the virtual side of things and hand those out to virtual machines. And then parallel serial ports, storage controllers, and then even a smart card reader. So again, we have tons of options to accomplish our goals. It just depends on A, what's the logical design? What's the requirement for the business? B, and C, what is the application requirement? So how do we fill those needs? So next up here, we're going to move away from the virtual machine, its configuration and content, and move over to the content library itself. So just as a quick refresher, content library is basically a way to organize ISOs, OVFs, and templates, and then synchronize them, if you choose, to other content libraries that are attached to other vCenters. You can have a local content library, which is basically just where I store all my stuff. good times. If I have multiple vCenters, or if I do not want to silo off that content library, I can create a subscribed content library that can be replicated to other places. It keeps images synchronized between or among different vCenters. So if I change one template, I don't have to copy it to 4 different data centers or 4 different content libraries. I can just let content library take care of that for me. And then I have the option of only download when needed or synchronize immediately. A good distinction here is that in 5.5, content library required you to download everything immediately. So anytime anything changed, it would pull over. In 6.0 and onward, that is, now you have the option to only download when needed. So it's going to exist on a local file system, NFS data store, or a physical data store. You can choose that when you configure, and then you import any of those items from a local file, URL, or you can even clone from an existing virtual machine or template. So what the heck do I put in there? Well, I clearly have templates, and if I don't, I should, because if I'm creating virtual machines, templates makes everything easier. Windows and Linux images are going to be maintained from a centralized point and make my management easier. And at that point, if I put them in the content library, like I said before, I only have to manage one image or a few images versus those few images over however many data stores, or however many data centers, rather. VApps that are commonly deployed. So if you don't work with VApps today, a VApp we're going to get into a little bit later, actually next couple of slides. But good ones to note are network load balancers, so virtualized NLBs, firewalls or proxies, such as Squid. There's a VApp for Squid proxy out there, and then third-party appliances. You may have in-band storage management or VSA or right. There's network introspection or IPS IDS. Normally those come in your OVF VApp flavors. And then ISOs are going to be, Windows 2008, Windows 2012, application images like SQL, etc. So anything that you normally use and mount to virtual machines, or if you have to mount to the host. You can also, and so Rebecca, correct me if I'm wrong, I think the ISO images in the content library you could actually use for VUM, is that right? I'm pretty sure you can. I'm forgetting
as far as I know, no. But I could very well be wrong. I'm pretty sure that was not a thing in 6.0, so if it is a thing, it's happened as a 6.5.
Okay.
But I'm not familiar with that concept being there.
Okay, so scratch that, reverse it. The way I was going with that was more of we can try to synchronize ESXi images across that as well, which is possible, but at that point you'd have to download it from the content library, re-upload it to your local VUM, and then leverage it. So good way to pass images from data center to data center without a whole lot of heavy touch. So what are the use cases for VApps? We just heard about OVFs, OVAs. VApp is a virtual appliance. It can be a single or multiple virtual machines within that VApp container. I manage resources for this group. So if you're familiar with resource pools, a VApp is also a boundary for resources, only on a smaller scale. So I can create multiple VApps, and they can all be peers of each other, and they can have reservations, limits, and shares for that group of virtual machines. Normally that grouping is going to identify a tiered application or VMs that rely on each other for some sort of either network communication or application functionality, whatever. The VApp doesn't keep virtual machines on the same host, mind you. The VApp just groups them as a logical entity. They do have startup and shutdown priorities within that grouping. So if I have a database, a web app, database app and web, I have the ability to start up that database first. I can wait for 120 seconds, or I can check if VMware tools are up, move on, next, right? And make sure that that integrity of that stack is maintained. I can give it vendor information. So if I'm a software developer or a software development shop, and I mean to distribute this as either advertisement or sale, then probably should put my name on it. Good idea. And then I can clone these. I can move them around. I can export them. You know, share, change, and move. I can also put them in the content library and replicate them. So this kind of reiterates what I said before. I won't belabor the point. Single or multiple VMs, multi-tiered VMs as a service. And then if you need a startup order or if you need any sort of IP allocation policies, that's what you're going to determine in a VAPP. So use cases for this, again, any virtual machines that are going to have any sort of logical entity together. So for instance, if I have a specific configuration that I want to deploy to multiple remote office, branch office configurations, I may ship a bunch of virtual machines down. Okay, well, they don't have any logical ordination there. There's no order, there's no focus. It's just a bunch of VMs. I could ship a bunch of ISOs and install everything from scratch. Well, that might suck. Takes a little more time and also more prone to human error. Or I can create a VAPP, I can export that VAPP, and then I have a consistent footprint everywhere that that VAPP lands. I know that everywhere that VAPP goes, it is exactly how I exported it until started up and reconfigured, etc. So anytime you need anything like that, right, the power of VAPPs is exporting, importing, transferring files around, and ensuring consistency. Suitability of VMware fault tolerance or third-party clustering. Well, what we're talking about is availability. So first off, if we're talking about availability, what is the level of availability that I require and from what resource? You can't just say, I need this to be up. Okay, what is this? What is up, right? So what tolerance do I have for downtime? Is it the application that has to be up? Is it the storage that has to be up? What are my availability levels? What are my requirements? Can HA provide what that workload needs? I've seen a lot of cases where people go towards software clustering or VMware fault tolerance as a means to provide the availability that even VMware HA may already provide. So keep it simple, stupid. Don't go for the advanced stuff unless you really need to or unless it's a requirement from the application business side. Fault tolerance, just as a refresher, we create a shadow virtual machine that is going to be an identical twin for all intent and purposes, aside from the fact that it cannot talk. So for those of you with twins out there, if you ever wish that your twin would be mute, this would be your ideal lifestyle. That secondary VM has all outputs suppressed. Only the primary VM can talk on the network or storage. There is a fault logging network between the two, so keep that in mind. That's something that really kind of dictates your design here. And then also vLockstep tries to keep everything near in sync, if not exactly in sync, so near zero downtime. This is great for no clustering applications. So if I have a third-party or homegrown application that I want to protect, and I want to have a higher level of availability than HA, then fault tolerance can provide that. So again, there are caveats here. Enabling fault tolerance does reserve all your RAM. You have a limit of 4 vCPUs. We already talked about the fault tolerant logging mechanism. You may have to shoehorn that in if you've already got a network that's deployed and your fault tolerant network is not created. So can become an issue. It does also introduce some latency, which is interesting, but the fact of the matter remains we're keeping track of all I/O requests from that virtual machine and we're duplicating those to another virtual machine. So just even the logging of those IOs creates a little bit of latency variability and a little bit of jitter that if you have, like we talked about before, latency sensitive virtual machines, that, that VoIP server, that high frequency trading server, that in-memory database may potentially suffer because of that that added latency. I said may decrease performance marginally. Again, emphasize marginally. This is not huge, but it is noticeable if you have latency sensitive VMs. And then we don't protect against OS or application failures because this is just making sure the VM survives. So if I blue screen on the primary, the secondary blue screens. If I make a wrong commit or some sort of configuration change on the primary, that change is replicated to the secondary. So keep that in mind when using fault tolerance. This is not an application protection so much as a virtual machine protection mechanism.
I do want to interrupt for a second with fault tolerance, if I may.
Go for it. No.
So, the underlying mechanism for fault tolerance changed in vSphere 6. It's no longer called vLockstep. It's fast checkpointing. So it's a more scalable technology. So this picture is a little bit out of date. And the second thing to kind of point out, besides that we're not using record and replay technology, it's more like a vMotion that never ends. Is the kind of a good way to think of fast checkpointing. And the picture also specifies single copy of disk.
Single disk. You can use multiple disks now, yeah. Or separate disks.
In vSphere 6, you can have the disk stored. I should say a copy of the disk stored on 2 different data stores.
Yeah. So, and that's important to note too, because the kickoff of this, when you enable it, just like you said, it's a special form of vMotion that's going to shoot across that fault tolerant. It's going to start with the management network initializing that connection. Then it's going to go over the fault tolerant logging network, and then make sure that that RAM is in step. And also, it's going to do that disk coordination. So if you're not sharing a single disk, you can have 2 different data stores. And that's going to start sending the writes over and making the changes on the destination disk too. So good call. This one was a little old, so I appreciate you calling that out.
No worries. I believe also, I could be wrong on this one, but I'm pretty sure there's a bandwidth requirement in vSphere 6 for FT that you have to have at least 10 gigabit Ethernet.
So yeah, that's
a supportability thing, not necessarily a functional requirement, if that makes sense.
Yeah, the requirement for a 10 gigabit network is not dedicated necessarily to the fault tolerant network, but it is, they don't want to see this. VMware doesn't want to see this on a 1 gig network. That is absolutely correct. So, it's been a while since I've looked at the requirements from a hard limit on fault tolerance. I know it does vary depending on your workload change. So. So anywho, just note that a 10 gigabit network is required on the back end for fault tolerance and low latency as much as we can get. So mentioned before, may add complexity to brownfield deployments we already saw this slide. Bye. Next. Third-party clustering solutions. So basically from an OS level clustering, from a clustering perspective, you have OS level, application level, or distributed/disparate, and I put clustering in quotes. This is a way to provide resiliency and uptime through either the operating system, so Windows and RHEL clustering, the application level, which you can do with Oracle RAC. Active Directory kind of does this. It depends on what we're talking about. But let's say Active Directory authentication, you can have active, primary, secondary, tertiary controllers, etc. So with that respect, they are application level clustering and they're replicating data between nodes. And then distributed disparate is more going to be I've got multiple VMs in a web tier. I'll throw a network load balancer in front of them. That's going to take incoming requests. That web tier contacts a virtual IP on another network load balancer to an app tier with multiple VMs, and then that app tier in turn has a VIP, goes to a database tier or database cluster, what have you. So this is another way of providing availability. I wanted to point that out. That's not necessarily clustering per se, so much as it is a distributed architecture, and it's more node based. So that is possible. It's just, again, with that distributed model, you got a network load balancer, you got multiple virtual machines. So you've got a lot of architecture here. So that may add cost. Application level clustering, you may run into more cost there, right? Because Oracle RAC isn't cheap. VMware fault tolerance comes in standard and enterprise, but we only have 2 virtual CPUs, when Enterprise Plus has 4 vCPUs. You know, the difference here as well, fault tolerance is I create a network behind it, and then I ensure I have capacity, which is 1 VM worth, whatever that ends up being, and then I right-click enable fault tolerance. I go through a little wizard, check, check, check. I don't have to know Microsoft clustering. I don't have to know Oracle RAC, right? So those are the trade-offs for your advanced skill sets there. Your integration of the existing design. So if I'm not already designed, brownfield, right? Fault tolerance needs to be created, shoehorned, etc. Your latency and performance can cause problems if you have any existing in your network or compute. So, and then understand your availability levels, know which resource you're protecting, know how much, if it's just the VM, fault tolerance, done and done. If it's the application, well, can we protect it through fault tolerance, knowing that we may have some application or OS config problems? It's for the business to decide, right? It's not our requirement to meet at that point. We've proposed a solution, but the business needs to okay that. That may be a risk. So, et cetera, et cetera. And then, do I need to protect within one data center among multiple hosts? Do I need to protect across multiple data centers? Those options change your design drastically. So keep those in mind. Determine the impact of scheduled guest activities. So what type of activities, you say? And I say, so much room for activities.
Do we just become best friends?
I think we did. Do you want to go do Kung Fu?
In the garage? Yes!
As soon as I saw scheduled activities, I was like, there's so much room for activity.
You read my mind on this one.
So what are the activities? What's the scheduled activity? Well, so in Unix, Linux, it's anything in cron, right? In Windows, you've got Windows Scheduler, you've got AT. You've also got third-party solutions like antivirus scans. I've got backups. I've got stored procedures for SQL or regular running jobs on any number of systems. So great. But first, what's my schedule? How often does that actually run? How big of an impact is that? And how often do I need to meet that? And then which resource or resources do I impact? And then same thing as before when I'm looking at meeting the resource requirements, what do I need to hit? Do I need to hit 100% of the peak? Do I need to hit 95th percentile over 30 days? What is that? What is that duration? What is that target? So you may change, this may change your design considerations drastically, depending on, because this is workload, right? This is foundational. So if I've wrong sized my VM, we talk about right sizing. I have wrong sized, right? I have made my VM too small and it doesn't meet the criteria, but day to day, everything seems to be okay. But once a month, it just, hits a wall and all of a sudden everybody gets mad at me because we're not printing checks. Oh, okay, well, the financial application's running and it's end of month. Month end close, I got to get all that stuff out the door and, well, I need to right size my virtual machine. But that changes the design of my VM. So same thing with storage, layout or composition, IOs, throughput to storage, your network design, bandwidth, et cetera, et cetera. So 2 examples here. IO storms may create a bottleneck, and I need to either stagger my backups, I need to get a higher IO performing storage array, or I even offload my antivirus scanning to something like NSX guest introspection. So we have options, right? But in that point, it does change the design a little bit. And then nightly backups over the network. If I do a network backup, I'm going through a guest agent in the virtual machine guest operating system. that pulls all that data, either block by block or file by file, over the network. So now I'm in for it because I'm pulling all of that at once. Maybe I throttle my 10 gigabit Ethernet. What do? I either stagger the schedule, most people do. I can rate limit the traffic or QoS it on the network side, which is undesirable for backups. I can even select a VADP enabled backup software, such as Rubrik. And at that point, I request the highest of fives. So yeah, I mean, in both these scenarios, it's one of those, can we offload this? Can we change the way that we do things? How are we throttling these resources? So vFlash read cache, it's a cool one.
You weren't joking when you said this was the longest objective of all time.
It is. It really, I told you we had 13 things to go through, and I was like, dear Lord, I'm talking fast, and it's hard for me to get through.
I took a nap halfway through it. I'm awake now.
I'm sorry, I blacked out. Did I miss anything? What?
Continue, sir.
Onward to glory. So vFlash read cache requirements. So VFRC. When we talked about before, the host local swap cache, where we could dedicate SSD to vSwap files. Well, this is similar, but this is for active storage and for read-only storage. So vFlash read cache dedicates local SSD to being kind of a front-end read cache. So where this comes from, I have a high-performing virtual machine that is mostly read. So let's say it's a data warehouse application. I need to pull all of that data. I need to read the ton of it in, and I need it available as quickly as possible. Well, I could do that over the SAN. Maybe I throttle the storage area network. Or if I'm doing it over NFS, I flood my 10 gig network, iSCSI, same deal. Or, I put a couple of SSDs in this host, I cache all of that read data, and then I just pull it locally. So I abate the heavy read that I'm pulling from outside of the host. I'm avoiding the fabric congestion, and then I'm basically serving the virtual machine with low latency, high capacity disk. So down here I got read cache or write through supported. So write caching is not supported with VFRC. Use cases, so like I said, data warehousing, large BI instances. Anyone that deals with data cubes know you got a ton of data you got to pull through, manipulate. Great for BI, web proxy servers, etc. This is a way easier option than buying a new SAN or buying a new tier of disks or right? With the ability to pop open my host, if I have disks available, I can go ahead and say, yep, here's my SSD, throw it in the host, your read cache, go. I'm not buying a new EFD tier. I'm not buying a new L-Flash array. I'm not buying other stuff. So very cost effective. But again, read only. So this isn't going to really help us if we've got a high write workload like CRM or something of that nature. So again, know your workload, right? Two scenarios here. I've got data warehousing and then web proxy. The web proxy, we could even say, hey, we're never going to change the data on this proxy. We're just reading because this is all locked down corporate websites. Maybe I'm logging somewhere else. So 80-20 read-write split, read latency sensitive, and writes I don't care about. I just throw out there and I forget about them. So again, these two scenarios, you could really benefit from a VFRC front end, and you have a maximum of 16 terabytes per host that you could actually serve through VFRC. So that's a lot. it's a lot of disk. It's a lot of IOPS that you can front end. So any heavy read workloads that aren't serviced by their normal running arrays or normal data stores, this is a very viable option. So I think I'm only 17 minutes over. That's not bad.
I applaud you for that. Yeah.
Any questions?
It's been pretty quiet activity-wise. Oh, there is one question. It says, would you use vFlash read cache if you have an all-flash fiber channel SAN?
Yeah, so there's a use case there as well. Let's say I have an all-flash FC SAN, and I don't want to use the capacity. That's an expensive array. So at that point, okay, yeah, I've got a heavy read workload or multiple read workloads because I can do this on a per VM basis. And absolutely, I can go ahead and throw in VFRC to kind of abate a lot of that read workload. Not on a capacity side, but it's more of an IOPS performance side of things. Like, you bought that for performance, but if I've got a couple of VMs that are just sucking the life out of an AFA, VFRC is a great way to make sure that array lives longer. So absolutely, there's a use case there.
And I think another important point there would be that your vFlash read cache configuration on the per VM basis acts as a reservation, right? So it's guaranteed to that VM, so it's not having to share that capacity that it's using for caching with anything else. Whereas on the array side of things, it's going to be more of a share.
Yeah, well, and I do want to make an important point too, and that's a great call. The fact that all of these reads, we're technically duplicating blocks, right? So anytime I make a read, that's going to come through the ESXi kernel. It's going to grab it, it's going to throw it in the read cache, and it's going to, every block has kind of a timer, and I'm going to have a cache hit or miss, right? So we're not taking any blocks from the array. We're not really moving capacity per se. The capacity, if I have a terabyte of data on the all-flash array, that's a terabyte of data over there. I could have up to a terabyte of data in the vFlash read cache as well. So 2 terabytes of data total, essentially. But I'm not taking anything from the array and moving it to the host. I'm only duplicating that so I can have faster reads, and then not, I'm offloading the performance from the array.
Cool. That's the only question I see. Let me double check Twitter. But I didn't see anything about 20 seconds ago. Cool. Well, I believe that's all the questions we have. So thank you very much for your time, Mike. I'm going to go ahead and stop the recording so we can sit. Whoa.
You would have been disappointed without a Beyonce GIF.
Let's have that good shot of Beyonce before I stop recording.
Establishment shot.
Thank you, Mike, for presenting, and thank you everyone who has attended live and everyone who will watch this on YouTube.